All right, in this lesson, we're going to look at Pythagorean theorem. We're going to spend about 2 lessons on it, and then I'm going to give you a couple lessons that are just project work time. So you'll have some project work time coming up next week, and hopefully I'll have your assignment for those posted by the end of this week so that if you want to get a head start, you're able to. So most of you are probably fairly familiar with Pythagorean theorem. I find it's one of the topics that usually when we get to it, everybody's like, oh yeah, I remember that stuff, and it goes pretty easy for most people. But again, there's a few things that sometimes we need a little refresh on to remind ourselves. And there's also going to be some practical trade examples or some practical uses in the trade that I want you to make sure you understand, so that when you hear them come around block 2 that you're reviewing for, that you know what they're talking about and you know how to use those techniques or use those components of Pythagorean theorem. So what is Pythagorean theorem? So Pythagoras was a Greek mathematician, and he gave us a lot of our trigonometry. Something about Greek baths. I'm not up for a communal hot tub in the sunroom at the college, but perhaps after COVID's done, maybe it would make the math brains work a little bit better, because that seems to be what happened. Well, there's a lot of strange things that happened in the communal baths in ancient Roman times or Greek times. But one of the things that seemed to occur was people came up with fabulous ideas. And part of that was they discussed their ideas. So Pythagoras is one of these guys that thought a lot about math, thought a lot about triangles, and he gave us Pythagorean theorem. Important enough that it was named after himself. So Pythagorean theorem is a squared plus b squared equals c squared. Well, what does that mean? Well, what Pythagoras discovered, he discovered that if you took this side, so side A, and if we were to, and I'll kind of sketch on top here, if we were to make a large square, and because of space, I don't have room to make a square, so we had A by A, so this was A squared. And then you did the same thing with B. You make a large square, so it's B by B for dimensions. If you add those two areas up, you will get the same area as if you did the same thing on side C, made a large square on side C. So that is what, I don't know, I really don't know what possessed him to investigate those relationships so much. You must not have had bills like we have these days, where we actually have to hold down a good job. He must have been well known by some aristocrat who supported him in order to have the time to think through some of these problems. But that's what he discovered, and it's true for every right triangle. Now, there's a couple important things to notice. A and B we call the legs of a triangle, okay? And then C is our hypotenuse. So I think I spelled that right. If I do cursive writing, you might not be able to read it anyway. So C is always the hypotenuse. This is really, really, really important. Okay, and the other thing that's really important is you won't be given this formula. This is a memorize it. Now, because I'm giving you projects this time rather than tests, you're going to be responsible for memorizing it should it show up on one of your exams, okay? So this is a memorize it. You've got fair warning at this point. So your hypotenuse is always going to be opposite the right angle. So our right angle is our 90 degrees. I'll often put a little square in the corner to show. So this is a 90-degree corner, or a right angle. And if you go directly across from it, that's our hypotenuse. Pythagorean theorem only works for right triangles. So if you have any other triangle other than a right triangle, if it does not have one 90-degree corner, Pythagorean theorem will not work. So all of the trick that we're going to do in this course is all going to be based on right angle trigonometry. Now, sometimes we can have a triangle that doesn't have 90 degrees, and we can redraw it into 2 triangles so that we do have a 90-degree component, but we're not going to do that in just yet. We're going to save that for a little bit. But key points: you must have a 90-degree corner, you must have a square right corner, and C is always your hypotenuse, which is opposite the right angle. This is also always the longest side. And there are no exceptions to that. That will always be the longest side. So if you've done some math and you're looking for the hypotenuse and you get a measurement that's shorter than one of your other sides, stop, take a moment, and realize I've made a mistake. You put a number in the wrong place. Okay, so that's some of your key information about the question. You'll notice A and B are the two legs. They can be put anywhere. Doesn't matter which leg I call A, which leg I call B, but it is essential that C is the hypotenuse or across from that right angle. So one of the ratios that there are, we're going to check this particular ratio. This states that any triangle with a 3, 4, 5 side ratio has a right angle. Well, why is that true? How could we prove that true? Well, we know Pythagorean's theorem will work if we have a right triangle. So Pythagorean's theorem says that a squared plus b squared equals c squared. So let's call this A, let's call this one B, and opposite the right angle is C. And it's also the longest side, so it has to be C. Let's put that information in. So 3 squared plus 4 squared equals 5 squared. 3 squared is 9, plus 4 squared is 16, equals 5 squared is 25. 9 plus 16, 25 equals 25. It is true. It is a right triangle. So it's one of the things. But what they've discovered is the lowest possible ratio of sides that will make this Pythagorean's theorem true, any triangle for which Pythagorean's theorem is true. If you reduce the lengths of the sides, you will get a 3, 4, 5 ratio. So how is that useful in carpentry? Well, let's say you're building a deck, okay? Let's say you're building a deck. We're going to put one post here, and we've got another post out here, okay? And we have another post here. And I want to know, my question is this corner true? Is it true? So what you can do is you can take your rule and measure out 3 feet, okay? Mark it off. Measure 4 feet in this direction, mark it off, and then take a tape and measure the diagonal between these 2 points. If it is 5 feet long, you know you have a true corner. You could do the same thing with inches. Let's say you're building something small. Measure 3 inches on one side of the corner, 4 inches on the other side of the corner, and see if the diagonal connecting those two is 5 inches. In that case, you have a right triangle. So you know your corner is true, that the corner is plumb. Is that important? Well, if you're ever doing reno work in an old house, you might not be doing the cabinets. The cabinet maker will be really happy if things are true, or the person installing flooring. This is a really good check. We renovated one of our houses, so we're in our 3rd house right now, 3 houses in 10 years. But our first house that we renovated our basement. It was an unfinished basement, and one of the things that wasn't checked, there was a hallway that was framed up. And the first time I went down to check the work, I said, no, that's not square. I could tell it wasn't square. I could visually inspect it and see it wasn't square. And it was supposedly corrected. But you don't necessarily question the carpenter, especially when you're not a carpenter yourself. I know just enough to be dangerous. I know enough to know that is something being done right or not. But when we went to install the flooring, so we did that ourselves, and I enjoy installing flooring. I don't know if you like doing that kind of work, but I find there's something therapeutic about it. Maybe I'm in the wrong trade. Maybe I shouldn't be teaching. Maybe I should be working with my hands. But when we went to install our flooring, we discovered the wall was not square because our flooring, we had about an inch different from one end of a hallway to another. If we had checked using Pythagorean theorem, we may have noticed that the hallway wasn't square before we got to the final stage. Thankfully, it's a hallway, but what that means is the laundry room that's on the other side of it also does not have a square corner. And because it doesn't have a square corner, should the current owners decide to put cabinets or anything like that up, it's going to require some extra shimming, and it makes more work for the person that follows. So sometimes it's about being careful so that if somebody else is building on the foundation or on the work that you have done, that you know everything is true. So it keeps everything. But that's one of the places where the 3, 4, 5 ratio is used. It's often used to find out, is a corner a true 90 degrees? Is it square? And you can use any particular ratios. We're going to look at that in our next example. So the rest of this is just going to be some example questions. So this particular one, we're going to make use of the 3, 4, 5 ratio. Is this corner square? So what we want to do is we're given 4 different triangles and the dimensions of them. We want to find out, do these reduce to ratios that would give us a 3, 4, 5? So let's look at 18, 24, and 30. So if it is a 3, 4, 5, or we could say 4, 3, 5, either of those two ratios, then it's square, okay? So if that's true, then it's square. So let's look. We have 18, 24, and 30. What's the largest number we can divide those by? If you're thinking 6, you're right. So we're going to divide each one by 6. 18 divided by 6 gives me 3. 24 divided by 6 is 4. And 30 divided by 6 is 5. Yes, the corner is square because we have a 3, 4, 5 ratio of our sides. Another way to check would be just to put them into Pythagorean's theorem and solve them. But we're just using simple ratios. So 18, 24, and 30 will give us a square. It'll give us a right corner. The next one, 12, 16, and 22. The largest thing we can divide those by is 2. So we get 6, 8, and 11. We can't reduce this any lower, and it's not a 3, 4, 5 ratio. No, the corner would not be square in that particular one because it doesn't match Pythagorean's theorem. And if you plug that into Pythagorean theorem, 12 squared plus 16 squared will not equal 22 squared. Let's check out this one. Now this one has decimals in it, but the easiest way to handle this one is let's get rid of the decimals. So 1.5 doubled would give me 3. Well, whatever we do to one, we do to the other, 4 and 5. So yes, that's a 3, 4, 5 ratio. Very easy way to get to that, to check it. So that means if you're working with something very small, use 1.5 inches, 2 inches, and 2.5 inches. And if you can connect those, you know you have your square corner. And then we have 9, 12, and 15. Let's divide by 3. And we get a 3, 4, and 5. So yes, that would be a square corner. So you'll see any of those combinations that give you the 3, 4, 5 ratio means you have a right angle, which means you're going to have a square corner there. So if you want to test your skill in the compound, when you're out in the compound next, take a peek, do one of your corners, get a buddy. You might have to stretch your distance a little bit. So you can only be 6 feet. You have to stay 6 feet apart from each other. So maybe instead of a 3, 4, 5 ratio, you want to do an 8, 6, 10 ratio. That'll keep you 10 feet. That'll keep you 10 feet apart instead of 5 feet apart. But lay out in the shop and see how true is your corner. Just take a mark out one corner 4 feet, another corner 3 feet, and see do you have a 5-foot connection in the middle. Usually we'll take an extra person to do. Make sure your diagonal is measured really straight, and you can see how good your skills were. All right, now to get away from ratios and actually using the formula, I'm going to write down the formula every time we do the calculations with it, simply because I want you to memorize it. So in this question, determine the length of the hypotenuse in the triangle shown. Round your answer to the nearest millimeter. So the first thing I notice is we're going to need a conversion. We have 24 inches and 34 inches, but let's convert at the end. Okay, so we'll make a note to convert last. Why would I convert last? Well, the reason for converting last is I only convert one measurement instead of converting 2. So less chances for error. It also keeps our numbers smaller, which is easier for our calculator. So let's label our triangle. We'll write our formula down first. A squared plus b squared equals c squared. Now a and b are our 2 legs. So we'll say 24 is A and 34 is B. And this would be my right angle. So this is going to be C, my hypotenuse. It's also the side we're looking for. It's the only one we don't have a measurement on, so it's quite straightforward. Now we're going to plug in our information. So we have 24 inches squared plus 34. And sometimes it's easier to leave your units out. Just if it gets confusing or messy for you when you're writing, if you want to leave the units off, you can. You just have to make sure you keep track of what it was you actually put in. 34 inches squared equals C squared. Okay, so we're just going to put these two in our calculator. Make sure you follow order of operations. Your calculator should follow order of operations for you. So you're going to square the 24 and square the 34 and then add them together. And that should give you 1,732. That's going to be inches squared equals C squared. And then we want just C, so we have to undo the square, which means our last step in Pythagorean theorem will always be taking the square root. That's an essential piece. So we're going to take the square root of both sides. This leaves us with C. 1,732, take the square root of that and you get 41.6, and we're back to inches because Pythagorean theorem always only gives us a length. It won't give us this squared bit. And then we're going to convert. So 41.6 times 25.4 leaves us with 1,057 millimeters for our length. And that would be our final answer. Nice, easy calculation, nothing too complicated. Example 3, determine the height of the triangle shown. Round your answer to the nearest millimeter. So no need to do any conversions here because we have millimeters already. So let's just get our formula ready. A squared plus B squared equals C squared. Label our triangle. So there's my right angle, and this is C. We can call this A and this B. It doesn't really matter which one you label. So let's put our information in. So A squared, I don't know, plus 26 millimeters squared. And it's this whole thing squared, which is why sometimes leaving out the unit can be helpful. And then equals 45 millimeters squared. All right, I'll put brackets around them just so hopefully it doesn't look funny that way. All right, how do we rearrange this one? Now I'm going to give you a tip for rearranging this one that is helpful. You could solve some math at this point. You could find out what is 26 millimeters squared, write that number down, but sometimes the numbers get large. So we can move this whole section all at once. So we're going to subtract 26 millimeters squared. You'll notice I'm subtracting this whole term and I'm keeping the squared with it, minus 26 millimeters squared. It's going to make it easier to put into your calculator. So now you can do this in your calculator all in one step. It'll leave less rearranging, less errors writing down numbers. Because I did find when I skipped this, when I just had students figure out what the number was without rearranging first, especially when numbers were large, like if you had 1,000 millimeters, by the time you square that, you get a lot of zeros, and they were making errors counting the zeros. So this is, excuse me, a great little tip to use. So now we're left with A squared on this side, because this has gone to 0, equals 45 millimeters squared minus 26 millimeters squared. Throw those brackets on there just to remind us that we have to square the 45. So A squared is equal to, in the calculator, 45 squared minus 26 squared. You'll notice we're subtracting in this case because we're looking for one of the legs. So A squared is going to leave us with 1,349. And that gives us square millimeters. And then we take our square root, which undoes the square anyway. So A squared is equal to, taking the square root of that, leaves me with 36.7 millimeters for length. Is it shorter than the longest side? Yes, we have likely done our math correctly. Okay. If you accidentally added together at that point, you made a mistake and you added here, you would end up with A being longer than your hypotenuse, which doesn't work for us. Okay, that doesn't make the math true. So that's a little step to help you remember that it's always going to be subtracting one of the legs when you're looking for the other leg. not sure if I tongue twisted that for you or not. Example 4. The section of roof shown has a 5/12 pitch. So we're getting into a little bit of practical math here. If the run measures 6 feet 3 inches, what is the rafter length in feet and inches? So I want to know what's the rafter length. So that's our rafter length. We sure hope that this has been built square. We have a run of 6 feet 3 inches, and I want to know, okay, I don't need to know the height, but I guess I have to find the height at some point in order to figure out Pythagorean theorem, because Pythagorean theorem says I need A and B to find C. Okay, so let's label our Pythagorean theorem. A squared plus B squared equals C squared. So we'll call this C because that's my hypotenuse. We'll call this one A, and let's call this one B. Now we need to know A in order to find C. So we can find that out using our pitch. Pitch has given us some hidden numbers. So first of all, find A. This is kind of a two-step question. So we know we have 5/12 for a pitch, 6 feet 3 inches. Let's turn that all into inches first. It'll be easier to work with. So that's 75 inches. So 75 inches goes on the bottom because that's my run over. I'm going to change this. I'm going to use A as well, just for the sake of simplicity. And we'll put A on top. 5 times 75 divided by 12. A is equal to 31.25 inches. So now we can plug that in here. All right, so there's our value for A. Now that we have that, let's put it into Pythagorean's theorem. So A squared plus B squared equals C squared. So 31.25 squared plus B is 75 equals C squared. Combine those two together. Make sure you do the squareds first, and you will find that you get 6,602 equals C squared, and then we're going to take our square root. After taking the square root, you get 81.25 equals C. So this is the same as 81 1/4. Now, if you're putting that into feet and inches, 81 divided by 12 gives me 6.75 feet. So we know we're going to have 6 feet. 0.75 feet times 12 gives me 9 1/4 inches equals C. So that would be our final answer after we convert. All right. And if you're still struggling with any of those feet and inches conversions, again, please reach out to me and let me know. It is important that you know how to calculate those. You've done those last semester, so I'm assuming we're still seeing as you passed last semester, we should be able to continue using those skills and continue building on them without reteaching them each time. And I've got one more question for you. What is the perimeter of the trapezoid below? Assume the lower angles on each side are equal. So you're going to have a couple questions like this in SAM. They've been built in there for a couple of years, so we'll reuse them. In this particular question, you don't initially see the right triangles like you did in the last one. So in this question, what we're going to do is we're going to create a right triangle by just dropping our line straight down. Okay, so we've dropped our line straight down, and we need to figure out what is this side. Now you'll notice this side, if we drop that dashed line, we have a right angle here, so this is going to be C for hypotenuse. Now we need to figure out the other sides. Well, A is 20 millimeters off the center, so this must be 20 this has to be 20 as well. And if we want to find out what's this bottom piece here, well, 42 minus 26 leaves me with 16. So that's 16 millimeters to split between this side and this side. So we're going to divide it by 2, leaves me with 8. So that's going to leave me with 8 millimeters here. Okay, so now we have a triangle. We know our two legs of the triangle, and we can figure out what C happens to be. So putting it into our formula, A squared plus B squared equals C squared. So A happens to be, well, it doesn't matter what we call them. We can say 20 plus 8, so 20 squared plus 8 squared equals c squared. If we put that in, we get 464 is equal to c squared. Take a square root of both sides. 464, the square root of that leaves me 22 millimeters is equal to c. Now, millimeters in, I got millimeters out. So I'm looking back to what I originally calculated with, didn't ask for any conversion, so we can leave it at that. Now the perimeter. So this is 22, means this side is 22. So the perimeter is just going to be 26 plus 42 plus 22 plus 22. So again, we're going back to some of that old math, and it will keep revisiting. We'll keep revisiting that as we go, which leaves me with 112 millimeters. All right, so hopefully that has you in good shape there. You're going to have a few basic questions to calculate in SAM for your quiz. And then we're going to continue working with Pythagorean theorem into next week, just because it's such a vital piece of carpentry trade math.